Yeah, so in the last class we started the discussion of a solution containing non-volatile solute. Okay, if a solution contains non-volatile solute, then you can apply Raoult's law for that solution. So according to Raoult's law, vapor pressure of a solution containing non-volatile solute is directly proportional to the mole fraction of solvent present in the liquid phase. I have told you why we are taking only solvent, because your solution now contains non-volatile solute. So solute particles or solute molecules, okay, they do not go to the vapor state, right? Therefore the molecules which occupy vapor state are only solvent molecules, right? Therefore the pressure is only due to solvent molecules. That's why we are taking mole fraction of solvent in the liquid phase, right? So this is the Raoult's law we should use for solution containing non-volatile solute. Okay, is it clear, student? Any doubt in this?
No, sir.
Right? Yeah. Now we'll discuss about colligative properties. I have told you this is actually the last part of this chapter, but before going to see colligative property, I'll give some informations and then we'll proceed. Okay, the idea is this. Listen, I have already told you about molality, right? Molality, which is denoted by the symbol small m. Okay, what is molality? Molality is nothing but number of moles of solute, number of moles of solute divided by mass of solvent in kilogram. Number of moles of solute divided by mass of solvent in kilogram. This is what we call as molality. And I have told you in solution chemistry, number 1 we use for solvent. Number 1 represents solvent and number 2 represents solute. Wherever I put 1, it means solvent, and if you put number 2, it means solute. Okay, so number of moles of solute can be written shortly as N2. N2 means number of moles of solute divided by mass of solvent. I'll write mass of solvent as W1. W1 is mass of solvent in grams. Students, observe this carefully. In gram. If you want to convert this into kilogram, you have to divide this value by 1000. Am I right, student? Is this correct? We want mass of solvent in kilogram. Okay, but usually mass of solvent is given in gram. So to convert gram into kilogram, you have to divide the value by 1000. Right? So if I rearrange this, I'll get N2 over W1 into 1000. Here mass of the solvent is in gram. Okay, right? So this is a simple relation for molality. Remember this. Try to remember this. Okay, very, very important. For molality, you can use this relation. N2 by W1 into 1000 will give you molality of a solution. Right? So I'll just make you to remember the concepts we already discussed. Right? Then second important thing is about solute. Okay, very specifically solute. Students, observe carefully. In the forthcoming discussions, we are going to consider solutions. Right? in this solution I have told you your solvent is liquid, your solute is actually non-volatile solute, right? We are going to consider hereafter, we are going to consider only non-volatile solute. Okay, this solute may be an electrolyte or may be a non-electrolyte. Okay, see what I'm trying to say. The solute that we are using here, okay, the solute may be a non-electrolyte. Solute may be a non-electrolyte. Non-electrolyte means it does not dissociate, okay, to produce ions, right? It does not dissociate to produce ions, non-electrolyte. Or your solute may be an electrolyte. May be an electrolyte. Okay, see, solute is non-volatile. Non-volatile solute can be a non-electrolyte, can be an electrolyte. See, I'll give some examples. For non-electrolyte, we have examples like glucose, right? Sucrose, urea, sodium chloride, potassium chloride, etc., etc. These are all examples for, I'm very sorry. Yeah, these are all glucose, sucrose, urea. These are all examples for non-volatile solute which are all non-electrolyte. They do not undergo ionization. Okay, glucose, sucrose, urea, right? These are all few examples. We have lot of examples actually. I have given few here, right? These are all examples for solutes which do not undergo ionization. Non-electrolyte means they do not undergo ionization. For non-electrolyte, remember, degree of dissociation is 0. Alpha equal to 0. Because they do not undergo dissociation, so degree of dissociation for non-electrolyte is 0. Keep this in mind, very, very important. We are going to use it. Okay. Then, what is an electrolyte? Electrolyte will undergo dissociation and produce ions. Okay. So, for I'll give some examples for non-volatile electrolytes. Okay, we are focusing only on solute which are non-volatile, right? So here I have given few examples for non-volatile solute which are non-electrolyte. Now I am going to give examples for non-volatile solute which are electrolyte. Okay, examples are sodium chloride, potassium chloride. Okay, we have a lot of examples. Sodium nitrate, okay, etc., etc. These are all few examples for non-volatile solute, right, which are electrolyte. Okay, what is meant by that? They dissociate and produce ions. Right? Even electrolyte like acetic acid, right, formic acid, etc., etc. These are all examples for electrolyte which dissociate and produce ions. Okay, these are all electrolytes. They do not undergo any dissociation. Right? For electrolyte, students, observe this carefully. In the case of electrolyte, we have two. Let me write here. In the case of electrolyte, we have two. In the case of electrolyte, we have two. What are they? Number one, strong electrolyte. Number two, weak electrolyte. Strong electrolyte, weak electrolyte. Okay, what is a strong electrolyte? Strong electrolyte undergo complete ionization. Strong electrolyte undergoes complete ionization or dissociation. Okay, therefore degree of dissociation is 1. For strong electrolyte, students, keep this in mind. For strong electrolyte, degree of dissociation is 1. Whereas weak electrolyte undergoes partial ionization. Therefore degree of dissociation for weak electrolyte is less than 1. It is not 0. Less than 1 means don't think that it may have value 0. No. Value will be above 0 but less than 1. Okay. Value 0 means it is non-electrolyte. You know very well. Degree of dissociation. Alpha means degree of dissociation. If degree of dissociation is 0, we call the solute as non-electrolyte. If degree of dissociation is 1, it is strong electrolyte. If degree of dissociation is less than 1, then it is weak electrolyte. Okay, students, any doubt up to this? Any doubt?
No, sir.
Okay, right. Now, so these two things are very important. So you I have given what is the expression for molality, and I gave some examples for non-volatile solutes. Okay, non-volatile solute. Now we will start the colligative properties. Keep all these things in mind. We are going to utilize this, right, in while doing problems, right, and while attending some multiple choice questions, etc. Right. Now we'll start the colligative properties. Colligative properties. What are colligative properties? Right, this is a very important part in solution chapter. Okay, often you can expect questions from colligative properties, right, and problems from colligative properties. Okay, first of all, what is meant by colligative properties? Colligative properties, right here, colligative properties are properties of solution, colligative properties are properties of solution which depend only on number of particles of solute. Okay, which depend, I repeat, colligative properties are properties of solution which depend only on number of particles of solute, okay, present in the solution. Number of particles of solute present in the solution and does not depend on, right, and do not depend on nature of the solute. Okay, take down. What are colligative properties? Colligative properties are properties of solution which depend only on the number of particles of solute present in the solution and do not depend on the nature of the solute. Okay, your solute, nature of the solute means, it may be urea, or it may be glucose, or it may be sucrose. It does not depend on whether it is urea or whether it is sucrose or whether it is glucose. No, it depends only on number of particles. Okay, see what I am trying to say. Suppose I will take 100 for example, right? Suppose I have 1000 molecules of glucose. It's a non-electrolyte. I'll take 1000 molecules of glucose in solution in water. Okay, or in 1 liter solution, right? 1000 molecules of glucose in 1 liter aqueous solution. Similarly, I'll take 1000 molecules of, just for understanding purpose I am giving this, 1000 molecules of urea. This is also a non-electrolyte. Urea in 1 liter aqueous solution. Students, observe this carefully. I have taken two solutions. In one I have 100 molecules of glucose. In the other one I have 100 molecules of urea. Both are aqueous solution. We have same volume. If you measure some colligative property, okay, you take a particular colligative property and measure it, you will get some value here. Say I'll get some value, Z. If you measure the same colligative property for this solution, I will get the same value. These two are same. I will get the same value. Why they are same? Because colligative property depends on number of particles. Colligative property depends on number of particles. Does not depend on whether you are using urea or glucose. Okay, whether you are taking urea or glucose, it does not depend on nature. It depends only on the number of particles. That's the point you should keep in mind. Is it clear, student? Colligative properties depend only on number of particles. It does not depend on nature. Your solute may be glucose, your solute may be sucrose, your solute may be urea. It does not depend on that. It depends only on number of particles. Is this clear? Any doubt in this?
No, sir.
Right? So what is colligative property? Colligative properties are properties of solution which depend only on number of particles of solute present in the solution and do not depend on the nature of the solute. Okay? Yeah. So this is what is called colligative property. Now in colligative property we have actually 4 colligative properties. What are they? Number 1. There are 4 colligative properties we have. Right? So colligative properties. What are they? Number 1. We have 4 colligative properties. Number 1, relative lowering of vapor pressure. Relative lowering of vapor pressure. Okay. While writing, okay, for simplicity we can write like this, RLVP. Right? Just for our convenience I am writing. Okay, relative lowering of vapor pressure. I'll write shortly RLVP. Number 2, second colligative property is elevation of boiling point. Elevation of boiling point. Elevation of boiling point. Okay, it is usually represented as delta TB. Elevation of boiling point. And third one, depression in freezing point. Depression of freezing point or depression in freezing point. Elevation of boiling point. This is one colligative property. Depression in freezing point, which is usually represented as delta TF. Depression in freezing point, this is another colligative property. Then fourth one, osmotic pressure. Osmotic pressure, which is denoted by the symbol pi. Okay, these are the 4 colligative properties we are going to discuss. Relative lowering of vapor pressure, elevation of boiling point, depression in freezing point, then osmotic pressure. Okay, so let's start with the relative lowering of vapor pressure first. Okay, take down. We'll start with the first colligative property, relative lowering of vapor pressure. Right, the next page. So the first colligative property is relative lowering of vapor pressure. Relative lowering of vapor pressure. Okay, take note. Shortly you can say RLVP. Okay, right. What is meant by relative lowering of vapor pressure? Right. Listen. Suppose students observe carefully. For colligative property studies, okay, these are the things you should keep in mind. For colligative properties, listen, your solution contain a solvent which is usually liquid and solute. The solute may be solid or liquid, okay, whatever it is, but the solute should be non-volatile. That is important. For colligative property studies, always keep this in mind. Your solvent should be liquid. Your solutes can be, it may be solid or it may be liquid, whatever it is, but it should be non-volatile in the solution. That is important. Okay, this is first important point you should keep in mind. Second point, students observe carefully. For colligative properties, whether it is relative lowering of vapor pressure or elevation of boiling point, depression of freezing point, whatever it is, right? You must use dilute solution. That is another important point. Dilute solution. Okay, what is meant by dilute solution? Dilute solution means number of moles of solute. 2 means solute, right? Number of moles of solute should be very less compared to number of moles of solvent. Okay, so for any colligative property study, these two things you should keep in mind. Don't forget. Very important. Okay, your solution should contain non-volatile solute and the solution should be a dilute solution. Okay, yeah. Now let us start with the relative lowering of vapor pressure. First, I'll take a pure solvent in a container. Students observe carefully. I'll take pure solvent at some temperature T. Okay, you take pure solvent in a container, closed container. Okay, evaporation will occur first, then condensation will occur, then you will get equilibrium. After reaching equilibrium, you measure the pressure of the or vapor pressure of the solvent molecules which occupy above the liquid surface, right? So let the vapor pressure of solvent, let me represent this as P naught. So what is P naught, students? What is P naught here? That naught symbol indicate pure. P naught means vapor pressure of pure solvent, because we have only solvent now. Vapor pressure of pure solvent. Okay, now what I am going to do, in this container I am going to add a non-volatile solute. What will happen if I add a non-volatile solute, right? Okay, in the solution. If I add non-volatile solute, you will get a solution containing non-volatile solute. Okay, now we have solution containing non-volatile solute. Okay, we have added non-volatile solute, but I have told you in the last class itself, listen, here in pure solvent the entire surface of the liquid contains only solvent molecules. The entire surface of the liquid contains only solvent molecules. So more solvent molecule will evaporate. Therefore, the vapor consists of huge number of solvent molecules. So vapor pressure will be high. when you add a non-volatile solute, what will happen? Some of the surface are also covered. Some of the surface is also covered by solute molecules. But we have taken non-volatile solute, so solute molecule, they do not undergo evaporation. They remains in solution but cover some of the surface. Why? What happens because of that? If it covers some of the surface, listen, more solvent molecule cannot go to vapor state. Only few molecules of solvent will evaporate and goes to the vapor state. So here also, keep this in mind, student. Here also, only solvent molecule will go to vapor state, because your solute is non-volatile. Only solvent molecule will go to vapor state, but the number of solvent molecules occupying this phase is less compared to this. Therefore, let me call this as vapor pressure of solution. If I put simply P, it is vapor pressure of solution. P naught means vapor pressure of pure solvent. Okay. Remember, student, here number of solvent molecule in the vapor phase is less. Therefore, vapor pressure of the solution is also less. So remember, whenever you add a non-volatile solute in a solvent, vapor pressure of the solution will be less. Vapor pressure of the solution is less than vapor pressure of pure solvent. Note down. This is very, very important. Whenever you add a non-volatile solute, okay, in a solvent, and if you form a solution, vapor pressure of the solution, P means vapor pressure of solution, P naught is vapor pressure of pure solvent. Vapor pressure of solution is less than the vapor pressure of pure solvent. Okay. As students, turn on your camera. Everyone. Students, all of you, turn on your camera. Okay. So when you add a non-volatile solute, vapor pressure of solution is less than the vapor pressure of pure solvent. Students, in the vapor state, which molecules are there in the vapor state? In solution, which molecules are present in the vapor state?
Solvents.
Yes, in pure solvent we have only solvent molecule in the vapor state. Even in solution we have only solvent molecule in the vapor state, correct? We have only solvent molecule because solute is non-volatile. Keep this in mind. Okay. Now students, P means vapor pressure of solution. P naught means vapor pressure of pure solvent. Keep this in mind. Now, what is meant by lowering of vapor pressure? So, by the addition of non-volatile solute, vapor pressure is lowered. Correct? Vapor pressure of the solution become less, right? So, by adding non-volatile solute, vapor pressure is lowered. So, what is lowering of vapor pressure? Let me write here. Lowering of vapor pressure. Lowering of vapor pressure. What is meant by that? We represent this as delta P. Delta P means lowering of vapor pressure. What is lowering of vapor pressure? Very simple. Vapor pressure of pure solvent, which is high, minus vapor pressure of the solution. P naught minus P is nothing but lowering of vapor pressure. It's nothing but lowering of vapor pressure. Students, one important point you should keep in mind: delta P is not a colligative property. Is not a colligative property. Delta P is not a colligative property. Lowering of vapor pressure is not a colligative property. Relative lowering of vapor pressure is the colligative property. Okay. So what is relative lowering of vapor pressure? Let me define the next step. Relative lowering of vapor pressure. Relative lowering of vapor pressure. What is meant by that? It is nothing but lowering of vapor pressure, lowering of vapor delta P divided by vapor pressure of pure solvent. Students, observe this carefully. What is meant by relative lowering of vapor pressure? Relative lowering of vapor pressure is nothing but lowering of vapor pressure divided by vapor pressure of pure solvent. Okay, and now you know very well what is delta P. Delta P is P naught minus P, P naught minus P divided by P naught. So P naught minus P by P naught. Okay, and we also know that I'll keep this P naught as such. What is P, students? What is P here? What is P here?
Vapor pressure of solution.
Vapor pressure of solution, right? Vapor pressure of solution. According to Raoult's law, we have already stated this. According to Raoult's law, for a solution containing non-volatile solute, vapor pressure of the solution is directly proportional to mole fraction of solvent present in the solution. Number 1 represents solvent. Or I can also write this as P equal to P naught into X1. This we know. From Raoult's law we know this. I am going to substitute this here. So in the place of P, I am going to put this P naught into X1. So I'll replace this P as P naught into X1 divided by P naught. Okay, I'll take P naught as common in the numerator. If I take P naught as common, I'll get 1 minus X1 by P naught. P naught cancels, so I'll get 1 minus X1. Right? You know very well, for a binary solution, X1 plus X2 equal to 1, or X2 equal to 1 minus X1. This we know very well for a binary solution. Therefore, 1 minus X1 is equal to X2. Okay? Students, is this clear? Any doubt?
No, sir.
Right, so this is the expression for relative lowering of vapor pressure, P naught minus P by P naught. Let me write to the next page. So observe carefully. So relative lowering of vapor pressure is denoted as delta P by P naught. Okay, lowering of vapor pressure by vapor pressure of pure solvent. This is also written as P naught minus P by P naught, right, which is equal to mole fraction of solute, Okay, just now we derived, we have derived this. P naught minus P by P naught, it is called relative lowering of vapor pressure. This is equal to mole fraction of solute. Number 2 means solute, right? Equal to mole fraction of solute present in the solution. Okay, so this is the expression for relative lowering of vapor pressure. We also know that P naught minus P by P naught equal to, what is mole fraction of solute? Mole fraction is nothing but number of moles of solute divided by total number of moles. Total number of moles means number of moles of solvent plus number of moles of solute. Total. This is mole fraction, right? Students, I have told you for colligative property studies, 2 things you should keep in mind. What are the 2 things? For any colligative property study, 2 things you should keep in mind. One is solution contain non-volatile solute. And second one?
It should be a dilute solution.
Very good. It should be a dilute solution. Okay. So for dilute solution, okay, number of moles of solute is very, very less compared to number of moles of solvent. So if you compare N1 and N2 is negligible actually, negligibly small. Therefore, I am going to neglect N2 here. Therefore, I can write P naught minus P by P naught, okay, is equal to or approximately equal to N2 by N1. N2 by N1. Is this clear, student? Any doubt? Students, is this clear? Any doubt in this?
Yes, sir.
Yeah. P naught minus, what is P naught minus P by P naught? Left hand side. What is P naught minus P by P naught? Yes, students, turn on your camera. What is? Yeah, left hand side is nothing but this left hand side quantity, right? The left hand side quantity is nothing but relative lowering of vapor pressure. Relative lowering of vapor pressure, which is equal to number of moles of solute and number of moles of solvent. We usually keep solvent as such, right? We usually take water as solvent, we usually, right? And the solute you can vary. So what does this indicate? Colligative property depends on, depends on number of particles of solute. So relative lowering of vapor pressure is a colligative property because it depends on number of moles of solute or number of particles of solute. Students, any doubt in this? Now what I am going to do, see, I took non-volatile solute. I did not mention whether the solute is electrolyte or non-electrolyte. Okay, if your solute is non-electrolyte, no problem, you can keep this as such. But your solution may be an electrolyte also. Therefore, if you use electrolyte, number of particles will vary actually. Therefore, I am going to make a small modification here. Okay, so what is that? P naught minus P by P naught, this is called relative lowering of vapor pressure, is equal to, I am introducing a new term here, I into N2 by N1. I am using the same expression, but I have introduced a new term here, I. Students, I am using the same expression, I have introduced a new term I here. This is applicable for all type of electrolyte. For all type of electrolyte. Okay, keep this in mind. Take note. Where this I is called Van 't Hoff factor. This I is called Van 't Hoff factor. Van 't Hoff factor. Right? For non-electrolyte, students, for non-electrolyte, if we use glucose, urea, sucrose, right? For non-electrolyte, I equal to 1. Remember this is very, very important. For non-electrolyte, I is equal to 1. For strong electrolyte, I is equal to N. What is this N? This N is the number of ions, okay, number of ions that is produced from one molecule. Number of ions produced from one molecule. Take down. Students, keep all these things in mind. Very, very important. If it is non-electrolyte, I equal to 1. For strong electrolyte, I is equal to N. Students, this N is number of moles. This N is not number of mole, it is number of ions. Number of ions. What is meant by that? Suppose if we take sodium chloride, one molecule of sodium chloride will give one sodium ion, one chloride ion, right? So how many ions will get? How many ions will get?
2.
One molecule of sodium chloride will give one sodium ion, one chloride ion. So number of ions equal to 2. So N equal to 2 here. Right? If we take, for example, if we take sodium sulfate, Na2SO4, sodium sulfate will give 2 sodium ions and 1 sulfate ion. So I'll get 2 sodium ion and 1 sulfate ion. So N equal to 3 in this case. Okay, because these are all strong electrolytes, sodium chloride, sodium sulfate, these are all strong electrolytes. For strong electrolyte, okay, Van 't Hoff factor I is equal to number of ions produced from one molecule. Okay, what about for weak electrolyte? For weak electrolyte, okay, we have to find out whether electrolyte undergoes dissociation or association. Based on that, we have to find out. Okay, we'll discuss that, right, as we go along. We are going to discuss Van 't Hoff factor separately. At the time, we will discuss that. For weak electrolyte alone, okay, we have to check whether dissociation occurs or association occurs, because in some solvent, solute molecule may also undergo association. In some other solvent, solute molecule may undergo, same solute molecule may undergo dissociation. So whether dissociation occurs or association occurs, based on that I value we have to calculate. Okay, this we will do as we go along, okay, in our forthcoming classes. Okay, yeah. So keep this in mind. This is very important. Relative lowering of vapor pressure is equal to Van 't Hoff factor I into N2 by N1. Students, remember here, which is very important. What is N2 here? N2 is number of moles. Number of moles of solute. What is N1 here? N1 is number of moles of solvent. Number of moles of solvent. Keep this in mind. Very important. N2 is number of moles of solute. N1 is number of moles of solvent. Right? Take down. Is this clear, student? Any doubt? Okay? Yeah. This quantity, the left hand side quantity, it is called relative lowering of vapor pressure. This you can determine through experiment. It is an experimentally determinable quantity. You can determine through experiment. Okay, we have a method called Oswald-Walker method. Oswald-Walker method. Right? I'm not going to discuss the experimental setup, but I'll tell you, using this method, Oswald-Walker method, you can determine the left-hand side quantity experimentally. Relative lowering of vapor pressure can be determined experimentally by using Oswald-Walker method. Okay, take note. Right? Any doubt, students, up to this? Any doubt?
No, sir.
Yeah. Now, let me discuss some more information here. So the relative lowering of vapor pressure P0 minus P by P0. This is relative lowering of pressure, which is equal to Van 't Hoff factor I into number of moles of solute by number of moles of solvent. Okay. Now I'll keep this I as such. What is number of moles of solute? Mass of solute by molar mass of solute. Number of moles of solvent. Number of moles of solvent. Mass of solvent W1 by molar mass of solvent. Okay. Or I'll keep this one as such, W2 by M2. I'll bring this to the multiplication, so you'll get M1 by W1. Right? So P0 minus P by P0 equal to this. Take down. Students, what's the value of I for non-electrolyte? What's the value of I for non-electrolyte?
One, sir.
1. Remember that, very important. I value for non-electrolyte is 1. Glucose, urea, sucrose. Okay, these are all few examples for non-electrolyte. And what is the use of this formula? Students, if you know the weight of solvent and molar mass of solvent and weight of solute, using this you can determine molar mass of solute. So relative colligative property studies are very useful to determine molar mass of solute. Okay, suppose if I give some unknown solute, right, you can determine what is the molar mass of the unknown solute, okay, using this formula. Okay, colligative property studies are very useful for the determination of molar mass of solute. Okay, take down. Now I will give very important informations which is very useful for competitive examinations. Okay, if you write any competitive examination, then you can use this. Okay, listen. So here I said P naught minus P by P naught, right? Now what I'm going to do, I'll write P naught minus P. Instead of P naught, I'll put P. What is P? What is P naught, students? What is P?
Pure vapor pressure.
Yeah, P naught is vapor pressure of pure solvent. P is vapor pressure of solution. Okay, vapor pressure of pure solvent minus vapor pressure of solution divided by vapor pressure of solution. This is not colligative property. Students, observe this. This is not a colligative property. P naught minus P by P. P naught minus P by P naught is colligative property. Okay, this is relative lowering of vapor pressure. Relative lowering of vapor pressure. This is not relative lowering of vapor pressure. This is not relative lowering of vapor pressure, because I am in the denominator. I am having P, right? But this is very useful for solving problems, numerical problems. Okay, this is equal to, I'll keep this P naught as such. Okay, minus, you know very well, P is nothing but P naught into x1 according to Raoult's law. Similarly, in the denominator also, P naught into x1. I'll take P naught as common. So P naught cancels. Let me write once. P naught, if I take P naught as common here, I'll get 1 minus x1. In the denominator, I'll get P naught into x1. So P naught cancel. What is 1 minus x1? 1 minus x1 is x2 by x1. What is x2, students? What is x2? Mole fraction of solute, and x1 is mole fraction of solvent. Okay, and you can also write this as, what is mole fraction? Number of moles of solute by total number of moles. Okay, similarly, mole fraction of solvent, you can write number of moles of solvent divided by total number of moles. So this n total and this n total cancel. So you will get n2 by n1 again. N2 by n1. So take down students. Just copy down. This is very useful for solving numerical problems. Okay, so let me write to the next page. So what is said here? P naught minus P by P. This is not relative lowering of vapor pressure. Student, keep this in mind. This is not relative lowering of vapor pressure, but this is very useful for solving problem. Get N2 by N1. Okay, N2 by N1. What is N2? N2 is number of moles of solute. N1 is number of moles of solvent. Students, observe this carefully. I'll keep this N2 as such. N1, we can write N1 as mass of solvent in grams, okay, divided by molar mass of solvent. Okay, N1 you can write it as W1 by M1. If I bring it to multiplication, I can write this as, I'll keep N2 as such, into, I'll bring M1 to the numerator, M1 divided by W1, W1 in gram. Students, observe carefully. Okay, now what I'm going to do, I'll make some more simplification. I'll multiply the numerator and denominator by 1000. N2 into 1000 into M1 divided by W1 into 1000. W1 in gram. Students, do you remember what is this part indicate? N2 into 1000 by W1 in gram.
Molarities.
Very good. It is nothing but molality of the solution. So this expression can be written as molality of the solution into molar mass of solvent, 1 means solvent, divided by 1000. Okay, take note. This is very useful for solving problems. P0 minus P by P. P0 minus P by P. Take note. Small m indicate molality. Here small m indicate molality of the solution, and capital M1 is the molar mass of solvent. Molar mass of solvent. This is very useful one for solving problems. Okay, take note. Is this clear? Any doubt, students? Any doubt in this?
No, sir.
Right. Okay, then. So with this, we have completed relative lowering of vapor pressure. Okay. We will do problems once we complete all the colligative properties. Right. We'll do problems. Okay. Right. Then the next one, the next property is elevation of boiling point. Take down. Second colligative property is elevation of boiling point. Elevation of boiling point, which is usually represented by the symbol delta TB. Elevation of boiling point. Okay, what is meant by elevation of boiling point? Okay. Yeah, students, observe this carefully. This first I'll tell you some information about phase diagram of water. Phase diagram of water, because we use water as solvent for most of the colligative property studies. Okay, I am not saying that only water is used. No, other solvent also used, but mostly water. Okay, and you know very well water exists in three phases, right? Solid, liquid. Water exists in three phases. Solid phase, that is ice, then liquid water, and water vapor. It exists in three phases. Okay, the phase diagram of water, let me draw like here. I'll put pressure in the y-axis and temperature in the x-axis. The phase diagram of water, okay, is appear like this. Let me draw like this. This is the phase diagram of water. Phase diagram of water. Students, observe carefully. Very simple one, but very, very useful. Here we have ice, solid water. Here we have liquid water. I'll put simply water, liquid water. Here we have water vapor. Right? Along this curve, suppose I'll take this point as origin, O, I'll take this as O and this as A. The curve OA, along the curve OA, liquid water and water vapor are in equilibrium. Students, along the curve OA, let me write here, along the curve OA, along the curve OA, along the curve OA, right, H2O liquid water and water vapor, H2O vapor, are in equilibrium. Students, observe this carefully. H2O liquid and H2O vapor are in equilibrium. Listen, the temperature at which these two are in equilibrium, okay, is called a boiling point. If H2O liquid and H2O vapor are in equilibrium, we call this as boiling point. This is called boiling point. So along the curve, whatever point you take, listen, suppose I'll take some point here. I'll take some point here, right? This temperature is the boiling point of water. I'll take some point here. This temperature is another boiling point of water. Because for this boiling point, the pressure is somewhat low. For this boiling point, the pressure is high. So for different pressures, for different external pressures, there are different boiling points possible for water. You know very well, boiling point varies with the pressure, right? As the pressure changes, boiling point also will change. What is meant by normal boiling point? Normal boiling point is if the pressure is 1 atmosphere, right? If the pressure is 1 atmosphere, right? The boiling point at 1 atmosphere is called the normal boiling point. We say that it's normal boiling point, TB. TB means normal boiling point, which means boiling point at 1 atmosphere pressure. Students, keep this in mind. As you change the external pressure, boiling point of a liquid changes. Okay, so water, you can boil water, you can boil water at many different temperatures. At many different temperatures along the curve OA. But what is normal boiling point? Normal boiling point is 1. Okay, it is the boiling point when the pressure is 1 atmosphere. Okay, if the vapor pressure is 1 atmosphere, then the boiling point of water is the normal boiling point. Okay, students, any doubt in this? Any doubt? Now we are going to talk about elevation of boiling point. So this curve, okay, I am going to consider the curve OA alone for our discussion. I am going to consider the curve OA. Why I am going to consider curve OA alone? Why? Because along this curve, liquid water and water vapor are in equilibrium, right? At all points, right? Whatever point you take, at all points, liquid water and water vapor are equilibrium. So along this point, along the curve, if you choose any point, at that point water boils, depending upon the pressure. Okay, yeah. Now keep this in mind. Now we'll discuss our the colligative property. First, I am going to take pure water. It is not necessarily water. It is not necessarily water. I took water as an example here. You can take any solvent actually. You can take any solvent, but I took water because in colligative property studies mostly we use water. That's the reason. Okay, so let me take some solvent here. Pure solvent. Pure solvent. Students, observe carefully. Pure solvent has some boiling point, right? Normal boiling point. Let me represent that as T naught. So what is T naught, students? What is T naught? T naught is the boiling point of pure solvent. T naught is the boiling point of pure solvent. Okay, and listen, here you have vapor pressure, students. This is vapor pressure of pure solvent. Okay, now what I'm going to do, I'm going to add a non-volatile electrolyte. If I add a non-volatile electrolyte or a solute, if I add a non-volatile solute, okay, in this solution, if I add a non-volatile solute in this solution, what will happen? Yes, what will happen, students? Can you tell me what will happen? What will happen to the vapor pressure?
It will decrease.
Yeah. So this is solution. Vapor pressure of the solution, this is vapor pressure of pure solvent. Here vapor pressure of the solution is less than the vapor pressure of pure solvent. If vapor pressure is low, what about boiling point?
Low, sir.
Listen, students, observe carefully. External pressure is different, right? External pressure is the atmospheric pressure, which is 1 atmosphere, say for example 1 atmosphere. If you take pure solvent has some vapor pressure, which is okay, let me just give some value so that you can easily understand.
Sir,
Yes.
sir, what is T naught?
T naught is the boiling point of pure solvent now.
Okay, sir.
T naught is the boiling point of pure solvent. Now, to give some clarity, okay, I'll give this point. So first I'll take pure solvent, right? I took pure solvent. Assume that, student, for pure solvent, vapor pressure of pure solvent, say for example, vapor pressure of pure solvent is say 0.7 atmosphere. Okay. What is the external pressure? External pressure, that is atmospheric pressure. Atmospheric pressure is 1 atmosphere. Okay. So if you heat the solvent, right, it is very easy to get 1 atmosphere because it is 0.7. It is 1 atmosphere. Therefore, if we provide, or let me take this even 0.9. Okay, 0.9. This is 0.9. Vapor pressure of pure solvent is 0.9. Atmospheric pressure is 1 atmosphere. Students, when you'll get normal boiling point? If the vapor pressure becomes equal to the external pressure, okay, that is 1 atmosphere, you will get what is called normal boiling point. If you take pure solvent, initially the vapor pressure of pure solvent, let it be 0.9 atmosphere. Now, if I heat it, more solvent molecule evaporate. Okay, therefore vapor pressure slowly increases, and at one temperature, vapor pressure of your solvent becomes equal to 1 atmosphere, correct? That is called the boiling point of pure water. Let it be T naught. Now I'll take a solution containing non-volatile solute. Okay, so what I'm going to do, the vapor pressure of solution, you know very well, when you add a non-volatile solute, vapor pressure of solution will be if you add a non-volatile solute, vapor pressure of the solution decreases, right? It can't be 0.9, so it will be, say for example I'll take this value as 0.7 atmosphere. Now to get normal boiling point, you should change the pressure as 1 atmosphere. Here this is 0.9 to 1 atmosphere, less amount of heat is required, whereas 0.7 to 1 atmosphere you require more heat, correct? Am I right, student? This is already 0.9 in the case of pure solvent. So to get 1 atmosphere, you just provide less amount of heat. Less amount of heat is sufficient. That means boiling point of pure solvent is low. Just, okay, we are heating slightly, so you'll get 1 atmosphere. Whereas vapor pressure of solution, it is 0.7. To get 1 atmosphere, you should provide more heat, correct? Am I right, student? Is it correct?
Yes, sir.
Therefore, boiling point of solution, I am representing boiling point of solution as T. Boiling point of pure solvent as T naught. Remember, boiling point of solution is high. Why? Because you have to provide more heat. So remember, T is greater than T naught whenever you add a non-volatile solute. Okay, addition of non-volatile solute. Addition of non-volatile solute. If you add a non-volatile solute, addition of non-volatile solute in a solvent, what will happen? Boiling point of solution. This is boiling point of solution, and this is boiling point of pure solvent, boiling point of pure solvent. Pure solvent. Boiling point of solution is greater than the boiling point of pure solvent. Okay, take down. Is this clear, student? Any doubt in this?
No, sir.
Yeah, take down, take down. So remember this, whenever you add a non-volatile solute, boiling point of solution become high. Vapor pressure decrease. Okay, vapor pressure decrease, boiling point will increase. Okay, and take the difference T minus T naught, that is called elevation of boiling point. So what is elevation of boiling point? Let me write the next page. So elevation of boiling point which we represent by the symbol delta TB is equal to boiling point of solution minus boiling point of pure solvent. Higher value minus lower value, always. Higher value minus lower value. So delta TB is boiling point of solution minus boiling point of pure solvent. Okay. Students, is this clear? Any doubt? Any doubt in this?
No, sir.
Yeah, right. Take two. Okay, ma. I stop here. We will continue. Next class I'll show you elevation of boiling point is a colligative property. We'll discuss that in the next class, and we'll discuss some more expressions in the elevation of boiling point. Right? Yeah, I stop here.
Thank you, sir.
Thank
So the next chapter in